Hi. Welcome to this presentation about Unicode and Cross-Site Request Forgery. Who am I? My name is Nestenius. I'm from Sweden, but I do it in English just to make sure we all understand each other. Just to be on the safe side. I've been programming since I was like 10 years old, and one of my biggest achievements in the past, I created my first website in 1996. That became Programmer 7, and that was my full-time living for about 7-8 years. And doing all the development, management, sales, administrations, and building a community. So it gave me a big experience on how to build on the web and how dangerous the web can be at the same time. I also been co-founding an Edgement AB. It's a Swedish consulting and training company. And I left it for about 1 year ago. And besides that, I also spent time on Stack Overflow, trying to help others, especially around security and OpenID Connect and OAuth and that topics. In the past, I'd done a lot of weird things. I did some gaming when I was like 15, 16 years old. I've been doing some demos on that OS computer. I also did some hardware hacking. This picture shows my, I wanted to make games, and game development is of course fun, but doing games on a PC or home computer is a bit boring. I want to make games for real TV games, but I didn't have any equipment, so why not build my own? So I reversed engineered the Sega Mega Drive and built my own hardware developer kit so I could program it from my Atari ST. That's one project, and another one is I created with a friend. We wrote a sound tracker for Atari ST computer, and I actually sold it in the shops. So this is back then, 1991, as you see here. It's pretty kind of old, and it was kind of written in 100% assembly language. So just for the sake of it. Today I work as a freelance instructor, consultant, and I do teach secure development at Lund&Bendsen. But my main focus is on training, is all about C# and .NET, web security, software architecture, and also about OAuth and OpenID Connect. That's my kind of 4 special areas that I focus on today. And if you want to connect to me, there's also links to my web and blog and my LinkedIn profile. So let's talk about, and also, interrupt me with questions. We have the microphone box that you can, raise your hand if you have any question. Yes?
What's the first game? Was that Silkworm?
The first game here was never kind of released. It was kind of, gotten maybe halfway through, But it was fun to write things. So I really like that. So today we will be talking about, first of all, Unicode and characters. And of course, how hard can that be? But that is really a difficult area, but I want to kind of explain how it works and also look at why it's related to security. That's the first part. And in the second part, we will talk about cross-site request forgery attacks and how to prevent them. So what are the problems with characters? I mean, we use characters all the day, and we use emojis all the time, but things does not really sometimes doesn't work as expected. So for example, if I go to C#, I have I can make a character, and I can copy this small emoji character. I can place it in here. An emoji or character, I mean, it's a character, it's a Unicode character, so that's fine. But this one, if I take another one and I copy this larger one, it will not work. It will give me a compilation error. So, I mean, character is character, but that one does not compile. So the fun thing in this case is that I need to make this into a string instead. And I, add the quotes around it. And the question is, how long is this string? How long do you think this string is? 2? Yeah. So this one is actually, if I run this code, it will print out that that string is 2 characters long. So that's one, problem. But it's a bit weird, but okay, it's 2 characters. We take another example. I have 2 kind of inputs here. One, emoji character here, and I have a string like that. We can remove this one. So the question is, of course, how long is the string? And someone might, choose that, oh, this is just, maybe 1 or 2 long. And this one is obviously 5 characters long, 1, 2, 3, 4, 5. But if we start and run this code, we see that if I run those 2, we see that in this case, the first one is actually 5 characters long, and the second one is actually 49 characters long. Kind of, what's going on here? Does not make sense, And of course, we can always look at, we can open this source code file. Let's say we open it in Notepad++. We know that program, we trust it. And it all looks well, 5 characters here, there's 1 character here, Weird. Okay, so let's look at Notepad, classic Windows Notepad. It's always been trusty, Nothing. The same, How can this one be 45 characters long and this one is 5? So if we go back to Notepad++, change the encoding, we see that, oh, this one's pretty big. And in this 1, 2, 3, 4, 5 example, we see that there's characters in the string that takes space in memory, but it's not visible on the screen. So we start maybe to see a feeling that we can use these things to make pretty interesting kind of security problems. And lastly, many of you here are consultants. And of course, writing code like that is kind of creates job security. Nobody will ever be able to understand this code, because if you run this code, you would see that it, of course, prints out and compiles, of course, and it prints out 30 in this case. But how can we have 2 variables? That does not make any sense. So let's go back to characters and try to understand what is the problem here, or how does this really work under the hood. So first of all, we use bytes as the fundamental unit of storage in memory, on disk, and when we send information on the internet. I think we can all agree on that. And 1 byte can contain a value between 0 and 255. That's awesome. We can all agree on that. That's good. But the problem is that in the world today, we have many kind of character sets. We have kind of Swedish characters, we have Chinese, we have Arabic, and we have the emojis. And clearly, we can't fit all of those characters inside 1 byte. So that's one problem. So somehow we need some character set to map between those characters and give them some number. So we have a character map that takes what we think is a character and give it a number. And that's great. And we all, I think, know about the ASCII table and ISO 8859 and Windows 1252. I think we all have seen those. So the ASCII table, the famous American one, it has characters from 0 to 1 to 7. That's awesome. But for us Swedes or Danish people, our characters is not part of that map, so we can't use it. So we can always use ISO 8859, and that's 1 byte per character. And we have support for our kind of characters down here for the and other kind of characters. Awesome. And there's also Windows 1252 that is almost the same as the previous one, but we have a different set of characters here in the middle. But still, this map does not cover the Chinese or the emojis, so we still have some problems. And one of the problems is called Mojibake. So what is Mojibake? Well, I think we've all seen and experienced that when we take some text as an input, we send it, but on the receiving end, we see something else. We see all those kind of characters, and I think we all have seen those characters back from now and then. And that is because the receiver and sender does not agree and use the same character map. So that's a kind of core problem. So, and we call that emoji bucket, the garbage that we get when we don't use the correct encoding. So that's actually a term for that, a Japanese name. So that's can be good to know. So the solution is Unicode. So the question is, what is Unicode? So Unicode is an effort to make a globally unique map of every possible character. So for each character, we give them a code point and a description. And in this map today, there's over 288,000 code points defined. So everything from emojis and similar things are mapped in this map. And we can actually see that map if we, for example, go to search online. We can see various characters. And all of them are characters in the emoji character map. And I can go in to any of them and copy it to Visual Studio and use it in my code, just like that. So that's awesome. So Unicode gives us a one true map that is universal and contains a map of every possible character, Arabic, Chinese, and emojis, and awesome. But we still have some problem because we need to talk about encoding as well. So clearly, all those 200,000 characters, we need to kind of convert them to bytes because 1 byte is not enough, so we need multiple bytes to hold each character. And okay, so how do we do that encoding? Well, there's many standards for doing that, and we will talk about UTF-8 and UTF-16. That's the most common ones today, but we as a developer need to be aware of. There are many other ones, and there's also additional ones that is more specific for different kind of applications, but we won't talk about those. Yes. So how do these encodings work? Well, in UTF-16, we use, as we see on this map here, we use either 2 bytes or 4 bytes per character, or 1 or 2 characters in Java or C#. So depending on the size of the value of the character, you will either need 1 char or 2 chars to represent it. And that is why, in my previous example here, this emoji here takes 2 chars in memory to be fully represented. So this one is 2 characters long. Okay, we can agree on that. But that makes things a bit difficult because we're used to use emojis every time. I mean, everywhere today. We use emojis when we chat and when we write text. So the problem here is that if I were to kind of do char first char equals so this character here is a bit corrupt because that character is, you could say, is half of the emoji, more or less. That's half of an emoji. That is more or less an illegal character. So our kind of representation of text and how we can cut in a string, or if we, for example, do hello like that, and I want to maybe take string first 5 chars, I could do like that, like substring from this string here. But now I get maybe I should take 6. So if I take 6 characters from this string, 1, 2, 3, 4, 5, I still will get the half of that string because this string is actually 7 characters long. And we can actually just kind of prove it just by running it to prove that this string that we get here, that length is as we see, it's going to start it, let's go through it, and we see that it's 7 long. So this string is 7 long, and if I will try to kind of cut in a string, and we have emojis or Unicode characters inside that string, we might get corrupt characters. So that's a problem, because how do we get the kind of 5th or 6th real complete character? That's a problem. And we usually use UTF-16 inside C# and Java and JavaScript in memory to represent text. So UTF-16, there's also kind of 2 variations. There's the big engine, little engine, and that kind of all depends on in which order you want the bytes to appear in. And that is all depending on the kind of CPU architecture on the computer that you're currently running on. So that all depends. But we also see UTF-8 as an alternative character encoding. And in this case, we use 1 to 4 bytes to represent one character. So depending on the size of the value of the character, we will need 1, 2, 3, or 4 bytes to fully represent that character. So this is a very space-efficient coding, because if we just send, English text like source code, we just need 1 byte per character. That's awesome. But if we were to kind of look for, emojis or Chinese characters, we would need 3 or 4 bytes to represent 1 character. And then, of course, the question is, when do you use what character? So the typical case is that you use UTF-8 when you store text on disk or send it over the internet. But in Java or C#, you usually use UTF-16 in memory. But there's also a trend to move towards to use UTF-8 everywhere, both internally in memory and also when you send it on the web. And then you don't need to do this kind of translation between UTF-16 and UTF-8 back and forth, so you would actually gain some performance. So in this case, so let's try one more thing. So if I take, yes?
You say you gain some performance, that's data traffic-wise?
Yes.
Performance-wise, inside the application, you might get some heavy problems with determining lengths of strings.
Yes, of course.
So there is a cost.
Yes. Yeah. But usually if you don't cut within the strings and you just treat the text as a binary blob of bytes, then, and as you said, yes, if you want to find the 5th character, you need to kind of count and to do it properly, because just taking the kind of 5th position, you will get half a character sometimes. So that's the kind of trouble. But so even in C#, so let's see here. One more question?
Yeah. Are you saying that Java has the same problem?
Yeah, I think we have a character in Java is 2 bytes. And you can't fit an emoji like this one in 1 character, because that's a value. So it's a good question. So if I look at a given, like a rocket here, or I can take an emoji character like whatever, like this one, it has, as we see here, its value is 128,000. And we know that, 1 byte is 0 to 255, and we know that 2 byte, a char that is 2 bytes, 2 bytes is 0 to 65,000, but still, that emoji that we have up here is actually, have a value like 128,000. So you can't physically fit it inside 1 char or character. That's simple. So you need 2 chars to fit it in memory. So that's the kind of challenge. So I'm just going to try one more, change one thing here, and not 7. So actually, in the latest C# 11, they have a new option to make a string to be stored in memory as a UTF-8 string instead of UTF-16. So internally, it's kind of stored as a kind of span, but we don't need to go into that. So in this case, this string will be, the length of that one will be 4. So you see that, but depending on the encoding, this one is 4 bytes long, bytes. But if we were to use this as a string, the length of that string, and we remove this UTF-8 here, we see that the same kind of, let's can we start? We see that the same kind of character here is either 4 or 2. So depending on the encoding, the size of it is different. In this case, the S is 2, chars. So one char is 2 bytes. So actually 4 bytes. And this one is actually 4 bytes as well, but still different encoding. So it's a difficult, how you think about these things. But we also see a trend, as I said, that more and more languages move to use UTF-8 internally as well. Okay, so this is encoding. Is that really a security thing? Well, the nice thing about all of the interesting part about these things, so let's look at that. So the biggest problem with Unicode is social engineering. That's one of the problems, because you can make links that looks valid but goes to some other place. So I want to copy this one. I want to use Chrome for this example. So I take view page source. So this first link here, if I click on this link, it does not go to, actually I will click it in Firefox. So this first link I have here, if I click on that one, I end up on a totally different page that actually I control. It's not up and running now. I don't know really why. It should be up and running. So let's.
It's serverless.
Yes, it's serverless. Always serverless. Let me just start that machine while we kind of just wait. I have a small virtual machine here that I want to kind of start. Okay. Okay. So the problem here with all of these kind of characters is the kind of social aspects. So if I view a page source of this page, I have, for example, here a link that almost looks like a normal link. It's go to TN data like that. But we see that, that's, a weird domain name. I don't know if that's some dirt on the projector, can we have it clean, that pixel should not be there, But, so if I click on this link, I actually go, so if I click on this link, I go to this site instead. So I was redirected. So it's a valid link. So this kind of weird looking link, so if I look at the source code here, it's a valid link that I own. But the interesting side is if I now look in a tool like Fiddler that can look at the traffic that is sent from a browser. So if I click on this link, I need to click on it on here. And if we look in Fiddler, we see that the actual domain that was kind of requested is xn, data okb.se. That's a real weird domain name. And in this case, so I own this domain, this weird looking domain I have registered. I own that one. And somehow the browser will, when I click on this link, connect to that weird link. So the browser is doing some translation of this domain that is used in Unicode into a format that works with the DNS and the domain name system. The same thing here. I have an Edgement domain. I click on that one. I need to kind of click on it in here to make it nice. And we see that it actually works in the address bar up here. But if we look in Fiddler at the traffic that is actually sent, we see that the link that was actually requested was that one. So that's interesting. So that one I also can own, that domain. But the interesting side now is that if I take this kind of weird kind of T character in the domain and I go to, I don't know, use it telia.com, for example. So I could create a phishing email to make a link that looks like a genuine Telia domain name, and I could actually buy that domain by registering that domain in the DNS system. So I can make links that looks like a Telia link that is really, really hard to distinguish from the kind of normal Telia link. And that is pretty kind of the scary part about the Unicode, that it can be used for social engineering to make links look okay. So that's one challenge. And there was also one link that didn't work before, so let's look at that one. This one here, so let's look at the source code first. So let's go to look at. So if you look at the page source, this link here looks like a Google link. You know, google.com/www.secure.now, clearly a Google link. But if I go back and click on it, I end up here instead on that domain. And that one I own. So this is not a Google link, it's a secure.now link. So in this case, we see that, the slash here is not the same as this slashes. So how could you actually distinguish that? So you can actually see that if you maybe go to Word and you paste that link in here, you see that depending on the font that is used, you can see that it's clearly a bit weird how it behaves. But using the right font, you can make a link that almost looks genuine. And that is the challenge today that hackers are using when they send out phishing emails to try to get you to click on weird links and ask you to log in with your username and passwords. And that's the kind of the biggest challenge today, that is really, really hard to create safe links that you can really trust. So sometimes it might even be better to just type it yourself than click on links. And finally, there's one example more on this page. I have an apple.com link here. Look like apple.com, but if I copy it and paste it, it goes to receive an Apple link up here, all genuine, but clearly this is not an Apple page. That's a really scary part. Questions on that? Are you all running away now? Yes, my microphone. Microphone.
Maybe you should explain a little bit about the concept of glyphs.
Yes. So, I mean, Unicode, there's different kind of layers in the Unicode standard. It's what we see as a human is something visible, and then you have the code points, the character that is combined of, and then we talk about how it's encoded in memory or on disk. So in Unicode, you can actually combine characters together in different ways. So, for example, if I go to this, I have a sample page here. So if you want to have like a family of people, you can choose, you can actually take two parent characters and 2 child characters and combine them together into a family character. And you can choose the hair color as well by combining different Unicode characters. So it's really, really a kind of a complicated and a complex way. And you can even be a bit crazy if you want to be, create Unicode that looks totally weird. That's totally fine as well. So it's a big world of possibilities, and at the same time, challenges on how to make it secure. And lastly, it's the kind of a human factor that, trying to make people click on links that you should not click on. So that's one scary part. And just to kind of summarize, so Unicode is all about the character map, that each character has a number and a description. And encoding is the kind of separate thing that talks about how we convert that character value to bytes on the disk or in memory. And also, our file is not just Unicode. It's all about the encoding that is used to store the file, UTF-8 or UTF-16 or whatever. And the length of a string is not always the same as the number of things you see on the screen in your editor. It can be totally different. And that's one approach that you can use to get through validation filters or similar. And just as Nick Craver, who's the lead developer on Stack Overflow, says that encoding is hard and we will ever, all screw it up, eventually. You had a question?
Yes. Is there a way to is there kind of DNA in each of the that you can look for in any file and determine which code page encoded this file?
It all depends. I mean, there's no like a magic header that says this is a UTF-8, UTF-16. There's one special character called the bomb character, byte watermark, that can use that can give us an indication if it's a UTF-8 or UTF-16, but it's not a required character for UTF-8, for example. And UTF-8 strings, if you just take a pure source code, it's the same as an ASCII table. It's 1 byte, 1 character, so it's hard to tell them apart. It's all when you come to the ORR characters that the length is different. So just to kind of to show you what to answer that. So if we take this file up here and I choose to just make a comment and I do and I take these characters here, and if we were to go back to disk and look in a hex editor, what's actually stored on disk? Now we really go down deep here, but just to answer your question, so as you see here, this is the same file as it is stored on disk. So it's actually 3 characters. It's a byte watermark character, but it's not even visible in the editor, but it's added to a file at the start. Not really required, but Visual Studio adds it by default. And we see that the ORR characters here is actually 2 bytes per character used on disk. And the slightly smaller emoji has 3 bytes. And then the larger ones has 4 bytes per character. But we see that the source code down here is 1 byte per character because it's English text. So that is how it looks like on disk when you store files today.
Just one comment for that. So even for files with no byte watermark, you can look at the bit patterns.
Yes,
and see it. So many editors can guess encoding for UTF-8 and UTF-16 just by looking at how the byte layout is.
Yeah, and as I said before, there was even some encoding called like UTF-7 and 8, and sometimes you could, before in the early days, actually fool many filters to use UTF-7 instead to inject evil things into HTML pages.
Just a war story that we had. I worked for a company and they distribute licensed software, and there was a file describing how many computers could you run it on and how many customers could it handle and what was the name of the ones who had purchased it. And this, the license was basically a digital signature for that that file, the configuration file. So they couldn't change stuff without that breaking. And it all broke down when somebody distributed a license file or a configuration file that accidentally had added the byte order marker or not added the byte order marker. I don't remember which, but
Yes.
that was totally transparent to the poor person editing the file, that they just broke the license key.
Yes. So it's complicated. There's a lot of kind of ways to but let's look at the second kind of security problem of the day, cross-site request forgery attacks. And it also is something that we need to get to take care of. So let's go back to the fundamentals of how a web works and how browsers work. We all know that the browsers keep a cookie jar of the cookies that is associated with each domain. I think we all know that. So if I go into surf to Google, the cookies for google.com is included in the outgoing request. And if I go to GitHub, the cookies for GitHub is included in the request. And when I go to some CNN or some news site, I will get the cookies for that news site. All well, all good. That's how the web works. But the scary thing is that what if I go to a bad page and that bad page asks my browser to make an update to GitHub? So let's say this bad page somehow using Ajax or JavaScript or somehow asks my browser, please update my email on GitHub. What will the browser do? Oh, the page wants me to make a request to GitHub, so let's include the cookies to that outgoing request. I want to be helpful. So just by visiting a bad page, I can in theory be hacked. And of course, it's not maybe that easy on just github.com, but in theory, just by going to a bad page, it can ask the browser to make a request to GitHub, and with that outgoing request, that my cookie to GitHub is included, so GitHub will think that, oh, here's a request that is authenticated, I know who it is, and I will change the email, more or less. Okay, that sounds a bit weird and odd, and I think we all really like examples. So let's make one more example. So let's say I log into GitHub. I will get a session cookie stored in my browser, and I think we all can agree on that. That is how the web works. When we sign in, we will receive a session cookie from GitHub. All is well. I go to a different page in my browser, and that one contains an image tag, like that, simple image tag. Okay, so the browser sees this image tag and it thinks, I need to make a web request to github.com, update email, new email. So the browser is helpful, makes the request to GitHub and includes my cookie. And in theory, just by going to another page, viewing a picture, an image tag, that image tag can make a request to GitHub in my name without me being able to stop it. I can't stop that thing. That's pretty kind of bad. So just by viewing an image, I could in theory be hacked. And yes, GitHub will not allow me to change the email that easily, but other services, devices, and sites will actually allow a GET request to make changes on the backend, depending on how the backend is implemented. So that's bad. But I really think that we need one more example. I think we really like examples here. So let's say I have a web HTML form for my bank. Awesome. I can make a withdraw, the amount, and to what account. Awesome. And if I submit that form will make a post request to the backend with my session cookie. That's okay. And the form data down here. All is well. Great. No problems. But the problem here now is, what about if a hacker steals that form and use it on some bad page? And the main problem here is that the backend here can't tell the difference between those two pages, those two requests, because they will look exactly the same. So even though if I go to the bad page and it makes me click on something so it sends a request to my bank, or if I really go to bank form and make a withdrawal here, the request that the browser makes to the backend of the bank will look the same. The same cookies, the same form data, the same user agent, everything is the same. And the backend can't tell the difference here. So that's really, really bad. So that's a problem. So we have two problems here. The first one is that the browser will, regardless of my interaction, if I enter a link in a browser up here, or if I click on a link, or I go to a bad page, or I click on a bad email, my browser will open and include my cookies in all outgoing requests. Yes, we are getting more and more features to fight this problem called same-site cookies, but we won't go into today. But it's one way to apply the same-site attribute on cookies to block many of those outgoing requests, or block the cookie to be included in those requests. But what we will talk about today is how we as a backend developer can add support to prevent these kind of attacks. So how do we solve that? Well, on a backend, what we need to do as developers, we need to basically, we want to be able to detect if the form submission that is sent to me actually came from my backend application. And we want to be able to block if the hacker sends a random HTTP request to the backend with my session cookie. We want to be able to separate the things. So how do we do that? Well, what we do is we generate that unique token. We set it in the cookie in the browser. We also add it as a hidden form field in the form. So when the user clicks on that form and submits a withdrawal of money, the post request to the backend will contain my cookie and this kind of secret value. And the big idea here is that the hacker will have problems guessing that value. And this is a way that we then can use to make sure that the form that we receive back actually came and was generated by our own backend and not generated by someone else. And the big idea is that the hacker can't get this secret value if we do a proper job and preventing, if you do a good security job otherwise. That's the kind of main thing. So that is, the CSRF attack in a nutshell. And I think my time is running up here. So do you have any questions on Cross-Site Request Forgery? Yes? Microphone?
Yeah. So this secret value is stored on the server side, right? So when it receives a request, it will look up this secret value, or how does it work?
You can do it in different ways. In this approach, you just compare the received form value with the token value, and if the token is secured, and you just compare that they match. That's the kind of simplest solution. And most backends today, both Spring and ASP.NET Core MVC, have support of this has built-in support for these kind of tokens, but you need to enable it properly to use it, but it's built in.
So I think you can think of this as a one-time key, so you can use it once. So if you try to use it again, then the request won't work.
Actually, to answer that thing, usually that token is the same for entire session, because if you generate new values all the time, then you can't go back or have multiple windows open at the same time. It will be kind of confusing for the user. So usually that token is the same during the entire session that you're logged in. And the big idea is that the hacker can't get that secret value, because if you protect the cookie properly and you do a good job otherwise on the page, the hacker can't get that value. Because in this kind of attack here, the hacker will, like in this one, the hacker on this side here will never see the cookie. He just going to remote control the browser to make a request in my name with my cookie.
But he can get his own cookie, right?
But he doesn't care that. He does not care about the cookie. He just wants to remote control my browser to make a request in my name, because when you're logged in, it's not me who's logged in, it's the browser that is logged in, and it has the cookies. And the hacker tries to control my browser or ask my browser to make a request in my name. Question?
So, this cross-site request forgery is actually enabled by default in Spring,
Yeah.
which is a pain in the ass, because I spent 3 hours trying to figure out why my posts are not
Yes.
working. But I actually disable it because I have a REST server. So my question is was that a good idea? Can I actually secure a REST service?
So, I have a slide for that, of course.
Thank you.
Yes. What about REST APIs? Well, the answer it, as the classic consultant would say, it depends. Of course. So if suspense. So if your API backend is secured by cookies, then you have a CSRF problem, because the problem with CSRF is that the cookies is added all the time by on outgoing request. And yes, if you use same site attribute on cookies, you could prevent many of those kind of attacks. But if you use an API that is token secured by using JSON Web Tokens, then it's not a problem, because in this case, you always manually need to add that. You always need to add that kind of bearer token. Let me see it like that. You need to add that header manually, so the hacker won't do it. Then the second problem is, do you really want to have tokens in your browser? That's a different question. But for the CSRF, whenever you have a cookie involved, you might be in danger.
I use the second option, so
Yes.
don't try anything.
But then the question is, should you really have tokens in the browser at all or not? That's a different question, because that is also something we try to move away from. Question?
Do you know the Greek question mark? Could you try Googling it?
It's a trap, yes. Of course. Reject, of course. That one, yes. It's a nice one. Called job security as well. So, last question here.
A little comment, maybe we should talk about later, but just as an information. 1 or 2 years ago, there came also news out about what's called BD characters in the encoding and so on. And they came with an example of source code where you have, like, you see the normal source code and there's nothing suspicious.
Yeah.
But because there was a Unicode BD character, it made a kind of backspacing all the way back,
Yes.
and overrode the real code that happened.
Yes.
So with a comment code.
Yes.
So you only saw a comment there, this is working fine, but behind it was like format disk or
Yes,
something
yes,
else,
yes.
or send the password.
So
and so on.
there's many problems, and you can hide things. And,
So
and
indirectly in source code.
yes. Question?
Sorry, I'm back again. Could you expand on why we don't want headers or tokens in headers? If you have the time.
You don't want to have tokens in a browser, because a browser is not a safe place to store tokens or refresh tokens, because the browser is insecure, or mobile applications as well. So you would move to something called backend for front end. That's more common pattern today that people are moving to put all the token handling in the backend and just use a session cookie between the browser and the backend. We can talk about that afterwards.
Faglig nu, der er ja, og som altid, da jeg har hørt på sådan en sikkerhedssnak, så synes jeg, at verden er blevet et lidt farligere.
Ja.
Så tak skal du have, Thor.
Ja, tak.